Hello, everybody. Thank you all for coming out to the Bexley Public Library. My name is Zach. I'm the programming librarian here. Afterwards, if you have astronomy questions, please direct them to the professional and not to me. Really quick, before we get started, this is a hybrid program, so we're happy that you're all here at the library. We also have people joining online at home, so at the end at the Q&A, if you don't mind just raising your hand, I will come around with a microphone. That way those joining online can hear what wonderful questions we're asking in the room. For those joining online, feel free to type any questions or comments into the chat at any time. I also want to highlight that this is the first in a series, so we will be back here on Thursday, July 17th at 7:30, and then again Thursday, July 24th at 7:30. And each program will have a different presentation, so it'll be a different talk. If it's clearer than what it is tonight, we might be able to bust out the telescopes at some time, but tonight is not looking promising. Also, speaking of telescopes, the library circulates telescopes that you can check out. So if you ever want to do any backyard stargazing, you are welcome to check out a telescope from the library and test it out. Tonight, we are again, really quick, I just want to give a big thank you to Wayne Schlingman and Dr. Stephan Frank for coordinating this series with us again. I think we're going on like 12 years or something of coordinating summer programs. So the Summer Astronomy series is always a wonderful series. So just a big thank you to Wayne and Stephan for coordinating that, and to the team at the Ohio State University Department of Astronomy. Tonight, we're very happy to be joined by Dr. Stephan Frank, who was born, raised, and educated in the south of Germany with a short but very meaningful interval in Edinburgh, Scotland, where he met his wife. He came to America in 2002 to continue a career in physics at the Ohio State University Astronomy Department in their graduate program, earning his PhD from OSU in 2008 and beginning his first stint as a postdoc led to his return to Europe, where he worked for 3 years at Marseille. And in 2011, Dr. Frank returned to OSU as well as Otterbein University, both in a research and teaching faculty with a focus on outreach and education to the public. So please join me in giving a very warm welcome to Dr. Stephan Frank.
Well, thanks, Zach, it's always a joy for me to come here. And literally, I can just walk here because it turns out that I do, in fact, live right around the corner here on Gould, because part of the reason that I came back to, that I came in first place, that I came back to Ohio State, is that my wife is actually from Bexley. So the Salmons, they've lived here their whole life, basically. So, okay. Catching my breath here from this little slip. Need to be careful. Ice hockey is not my favorite sport, actually. So, although we'll talk a little bit about ice in a few minutes. So, well, you've heard probably that going to Mars is, at least on some people's longer time horizon. And the idea is that, well, should we do this or should we not do this? More specifically, should we actually try to establish some kind of colony there so that people could potentially live there? This has been in the media, fostered, of course, by recent events. And so I will try to highlight some of the consequences that you will be facing if you really want to go and live on Mars today and come to a very clear conclusion whether this is possible or not at the very end. But I would like to start, like every German should, by actually introducing a board game to you. It turns out there is an amazingly cool board game that has exactly that topic. It's called Terraforming Mars. And I've spent hours and hours and hours and hours playing it. You actually can do that too, because I just checked with Zach. The library is also a place where you can check out board games. And they do have Terraforming Mars. So it's really, really great. It turns out, as you can see, this is not just Monopoly where you're moving around something. this is a little more complex and complicated. It really simulates a little bit of that. Scientifically, it's so-so, I would say. But as a board game geek, it's a great game. It's fun to play, and it's very tense. Takes about an hour or so to learn the rules, but once you get the hang of it, it's fantastic. So I always like to point that out. So, first question. Is there currently life on Mars? And of course, that is a question that has been asked, not just by us nowadays, but very famously by a great entertainer, the spaceman himself. If you remember, who remembers that song by David Bowie himself? Cool. Later on, can you tell me what that song is about? I have no clue. It's certainly not about living on Mars or anything, but it's a great song. I totally love it. And as you know, he was a really crazy character, and I could totally see him living on Mars, actually, as a Martian out there. He also was not the very first one to ask that question. So this the proverbial Martian is that extraterrestrial being that everybody has in their minds when they think about extraterrestrials or aliens, right? A Martian, that's what we all know, and we are well aware of this. And that goes back a long time. Well, being here in the library, I also always like to point out that there are very cool science fiction books about Mars. The proverbial Martian invasion prototype, War of the Worlds, a great book to read. Even nowadays, you can open it, and it's fascinating. It's wonderfully written. It has even been turned into a little bit of an operatic version. So if you've never heard that, it's really, really great. Orson Welles did a version where he put it in New Jersey, and it was basically like the invasion on the East Coast, and people were listening to it on the radio. So that the radio program is still available. You can listen to it, and it was a live show that he did. Allegedly, people panicked about this because this was around the time of the Second World War. Another great one that I always like to point out, and the library has all of these, by the way, so if you want, go ahead, check it out later on. I always love Ray Bradbury. It is less about science, but more about the psychology of someone living on Mars and what they would experience there. And therefore, this whole idea of, Martians that may or may not invade us has been sticking around in popular culture already for a very, very, very long time. Part of the reason for that is possibly a little mistake in translation, as it turns out. Around the middle of the 19th century, 1860 or so, 1870, this man, Giovanni Schiaparelli, a great astronomer working as the director of the observatory in Milano, trained his eye on Mars with a telescope. Remember, at that point of time, it turns out that photography wasn't in a stage where we would be using it for astronomy, and therefore you really looked through a telescope, and you had to describe what you see. And what he saw were these intricate features. He made little maps of all of this, and these features, they looked to him like they were linear, like little lines that were all over Mars. And he simply called them, in the paper that he described them in Italian, canali. Now it turns out that canali can be translated into English in two ways. You can either call it a channel, like the channel between England and France, and then everybody understands that, that is probably a thing that nature made. It's a natural occurrence because, well, that's what the channel between England and France is, right? It's not made by humans. You can also, however, translate it to canals. A canal clearly implies that someone has constructed that, right? It's an artificial structure that intelligent beings have made. And that is the idea that Percival Lowell took up, and he built a whole telescope site. He was independently wealthy, and he could build in Flagstaff a great observatory, which actually is the observatory where Pluto was discovered. So it had ultimately a really, really good reason. But what he did there for the last 2 decades of his life, he became more or less obsessed with this idea. And he looked at Mars over and over and over and over again, and he came up being convinced that there must be these canals. And he thought of them as things that were built for a purpose, possibly because he could also see that Mars had polar caps like the Earth, possibly to transport water and or ice from the high polar regions down to the mid-sections of the planet. And so he thought of Mars brimming with life and really intelligent life. And he basically made it his whole big purpose to bring that idea out into the world. And he gave many, many talks to the point where towards the end of the career, this became so much of an obsession that within the astronomy world, people were looking at him like, dude, I mean, maybe you're a little bit too obsessed with this, because it was already realized then that a lot of other astronomers, when they looked through their telescopes and later on took pictures, because that's about the time when you can now build cameras and you can take pictures, and you look at them and people are like, it's not exactly what we see when we look at Mars. It's kind of odd, but okay, well, I mean, Percival Lowell was a very well-respected astronomer, and so, well, who am I to doubt him, right? But people were, by the end, a little like, skeptical about this. And it turns out that, yes, a few years later, when we were able to actually go to Mars and send out spacecraft in the mid-60s and early 70s, it was realized that, oh no, these canals do not exist at all. Yes, there are surface features. There are surface features, as you can see, in low resolution in 1965. 6 years later already, look at how much of a difference it makes. 6 years, we have developed technology that can resolve these intricate structures, but they do not look like man-made canals at all. And furthermore, what was very devastating for the idea of there could be life on Mars was the fact that we measured in 1969 what the actual pressure of the atmosphere on Mars is. This is a famous diagram. We're going to take a look at this later on a few more times. It's called the PT diagram in physics, pressure and temperature. And it shows you under what conditions water can actually be in the form of either a liquid or ice as a solid, or in the air as water vapor, as a gas. And it turns out that here on Earth, where we have at the bottom of the atmosphere, where we stand, where we breathe, we have exactly one atmospheric pressure, and lo and behold, as you can see, this line goes through, well, if the temperatures are right, all three types of states of water can exist. And yes, I mean, the polar caps, ice. All of our oceans, water, liquid water. And, well, some of that evaporates, forms clouds, and we have water vapor, like today in our atmosphere. So that's great. But if we go to Mars, before we knew what the pressure of the atmosphere on Mars is, there was a little bit of hope that this could be true for Mars as well. But the actual measurements show that, unfortunately, we are here at this level, and what you see at this level is an interesting point. There is no possibility for liquid water. On the surface of Mars, water either has to be in the form of ice or in the form of a gas. It goes from one to the other and back and forth. This is called sublimation and desublimation, if you remember your basic chemistry. And that means that there is no chance whatsoever that there is standing liquid water on the planet Mars. We'll come back to this topic over and over again. So, wait a minute. Two really, really well-known astronomers that had discovered, Schiaparelli had discovered many, many asteroids and had cataloged comets and things like that. What were they seeing actually there? And it turns out that probably optical illusions. When you don't have super good high-resolution pictures and images, you kind of interpret whatever you want to see there. So our human visual system is actually really, really good in making patterns. There's this famous one that looked in 1976 like a little face that is staring at us, right? So this photo was taken, and here you have the two eyes, there's the nose, and half of it is in the shade, but that's clearly a face. And I remember there were books about this, Erich von Däniken, this UFO type of guy. He saw aliens everywhere, and that was one of his prime examples. He was like, they made a face on Mars to give us a message. Well, once we go there and we take a close-up picture and a three-dimensional reconstruction of it, it doesn't look like a face at all. It's just the image that you took here. Our brain tries to do that. It tells us, oh, look, looks like a face. This happens all the time. Here's the smiley face crater, because look what it does. It looks like a smiley face, right? Everybody looks at this and says, yes, this is a smiley face. It's not. It just happens to be that way. Or here, oh, the Mars heart. Oh, very nice. It's always great for Valentine's Day. It's just a pattern. Our mind sometimes wants to see things, and then we see them. That's just how it works. There's actually a word for this. I forgot what it is. There's a technical term for that, but that's what it is. Nonetheless, people then went and said, okay, well, there is probably no liquid water, but let's test it out anyway. And so in 1976, we had this Mars landers, Viking 1, Viking 2, and they had actually on board some kind of experiments that were trying to test whether there is at least some microbial life. I'm not going to go into the details of all of this, but this was 1976. This is now almost 50 years ago, and people are still disputing and discussing this. So in the realm of science, sometimes nothing is clear. And people are arguing back and forth, and it turns out that the experiments are not really conclusive. It's very, very hard to rule things in or out. Another interesting finding is here. When I first heard about this, I was just shocked. It turns out that it is possible for an asteroid to float through space, land on the Earth, becoming a meteorite, and then landing on the Earth. And we collected meteorites, and a few of those meteorites actually originated from Mars. When I first heard this, I thought this is a super crazy idea. I mean, next time go outside, when you see Mars, this little red point in the sky millions of miles away, how is it possible that a rock from there comes to us? It is. If there is an impact on Mars that kicks up lots of stuff, some of that debris might find its way here to Earth. And we have found not just one, but a few of them. This is the most famous one, however. So a very, very few. I mean, most meteorites are not from Mars at all. Some are from the moon, actually. But the overwhelming majority are just stuff that's floating around in space. But that one clearly comes from Mars. We know that because we can chemically analyze it. And it was reanalyzed a few years later. It's very old. And it's probably from a time when Mars actually had the possibility to have liquid water on its surface. And when people reanalyzed it, they found really strange stuff on it. Hydrocarbons and amino acids that resemble the amino acids and hydrocarbons that we have here on Earth in all living creatures. And taking a closer look, those shapes totally look like so-called terrestrial nanobacteria. Well, nanobacteria here on Earth are already the smallest bacteria that we have, and they're kind of really odd here on Earth already. But it turns out that the structures that we see in this meteorite are much, 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 much smaller than that. So it's not exactly clear what these things are, whether they were alive at some point of time or not. In any case, as you can see, this is tough. I mean, we are still grasping for straws, basically, but obviously this is not a totally well-developed Martian that's moving around and building canals. If at all, this is microbial life. But we don't even know whether that is the case or not. about 2004, there was a little bit of ballyhoo when people thought that, oh, look at this. There's evidence that there is methane in the atmosphere of Mars. That's odd, because it turns out that the conditions on Mars, in the atmosphere of Mars, are unstable for methane. Methane should decay in about 300 years into water and carbon dioxide. So it's not stable. The fact that it's there means that it must have been produced rather recently, well, in the last 300 years, because otherwise it wouldn't be there anymore. Methane here on Earth, well, if you walk around a swamp, right, you may smell stuff like that. And so there's definitely a biological pathway to create lots and lots of methane. And so people got very excited until many chemists pointed out that, oh, there are many other ways of doing this, as well as astronomers pointing out that, oh yeah, sure, if you get hit by a comet or you have some kind of volcanic outgassing, you will get methane right away as well. So it's not a telltale sign of life, but at least it's like, it's another hint that possibly there could be processes that produce that. So to summarize all of that, the current status is that we haven't found anything definitively. We cannot say whether there is life on Mars currently or not with great confidence. What we can say with great confidence is that at the moment there are only robots on Mars. There's not even a human being on Mars, but we have populated the planet Mars and its surface with robots. So it's the only planet that we know that is full of robots. And that's great, right? Because we do, reading the War of the Worlds, we do not need to fear an attack. Those microbes will not take over our beautiful planet Earth. Also, if we go there, we don't have to deal with big, difficult ethical issues that we may exterminate life there. No, if there is no life, then, well, we can colonize it, right, without any problem. On the other hand, this is really, really bad news. Because you can immediately see that, well, perhaps the conditions on Mars are such that not even microbes can survive. Now, if not even microbes can survive, like these tardigrades here, how would human beings ever survive on that planet? And that leads us now to the next topic, where we're going to take a look at, well, what makes actually Earth such a great place for life? And the key is that we have the perfect conditions. Earth is really a paradise for life. It's not too hot, not too cold. It's the typical Goldilocks problem, right? Everything has to be just right. It's not too hot, not too cold. The pressure here, I can nicely breathe. I'm not being crushed. On the surface of Venus, for example, the pressure of the gas atmosphere is about 60 times larger than here, which means that you're basically a deep sea creature a kilometer down in the ocean. Very hard to survive that. We have a little bit of salt in our oceans, but they're not overly salty. So, another interesting point is that we are being sheltered quite a lot from the harsh realities of the universe. Out there, the conditions are really, really bad. There's a lot of radiation, and we are mostly sheltered from this by this tiny little sliver of an atmosphere that we have. So the radiation background that we have is very, very, very low. That is good for life, and we'll come back to that in a few minutes. Furthermore, most of our planet gives you really, really great stable conditions, either on land or in the oceans, in the sea. It's not a hostile environment. Yeah, it changes from time to time, but not catastrophically. This is great for life, and it has been great. Well, but it hasn't always been that great. Earth started out in a period that's called Hadean, where life was impossible on our planet. During the first 800 million years of the lifetime of our solar system, the conditions were such that impacts of large asteroids and comets were so common, and these beasts were so large that that little thing that happened 65 million years ago that led to the demise of the dinosaurs, that happened all the time, every couple of years. and this was called the Great Heavy Bombardment. And at that point of time, Earth was basically mostly molten. It's hard to imagine that there could be any life, right? So nowadays, however, it's totally different. A big part in that plays our atmosphere. Atmosphere is crazily amazing when you think about it. It is a very, very, very tiny little sliver of gas that our planet keeps holding on to. And yet it is extremely important for all of us. Without the atmosphere, we wouldn't be able to exist at all. Not only because we couldn't breathe, but we will see that there are many, many other things that the atmosphere does for us that is really, really important. Now, when we look at the atmosphere, it's kind of an odd list. So an astronomer looks at this and says, okay, well, you take a parcel of the gas, you chemically analyze it. What's in there? Well, mostly nitrogen, quite a bit of molecular oxygen, a tiny little bit of water. Well, see the water vapor causing clouds. They're highly reflective. We'll come back to this a little bit later on, probably. There's also, interestingly enough, about the same amount of a noble gas, argon, in the atmosphere, and a tiny, 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 tiny little amount of carbon dioxide. Only about 350 out of 1 million particles is carbon dioxide. As an astronomer, you look at that list and you scratch your head and you're like, what the heck? This is a totally bizarre composition of stuff. Because as an astronomer, you're so used to thinking about what's the universe made of? Well, mostly hydrogen and helium. 98% of everything of the matter in the universe is hydrogen and helium. All that other stuff is very, very, very rare. But wait, let's go back to this list. Oh yeah, there is a little bit of hydrogen in the form of methane here and water, H2O, but tiny little amounts. It's mostly nitrogen and oxygen. That's weird. Why is there no hydrogen and helium? Well, it turns out that this has to do with basic physics and how massive the Earth is. Crash course in atomic physics. It turns out that gas molecules are moving around with a fairly high speed. They have a certain velocity. That velocity is related to the temperature. In fact, temperature is a measure for the average velocity of a gas molecule, but it also depends on the mass of the gas molecule. So don't worry about this formula. All that it means is that, if you heat up a gas, more and more of these gas particles will be moving faster and faster and faster. Likewise, if you have the same temperature and you have different types of gases, it turns out that obviously the lightweight gases at that temperature, they move around really, really fast. So as you can see here, hydrogen, a large fraction of all of the hydrogen molecules at these temperatures have a very high speed. The more and more massive a gas particle becomes, oxygen being 16 times more massive than hydrogen, the slower and slower they are moving around. Now, this is important because the Earth is desperately trying to hang on to this gas. How does the Earth do that? The Earth does it by gravity. But if you're going fast enough, then you may escape the clutches of the gravity of Earth. That's what we do with rockets, right? If you want to leave planet Earth into space, you have to build a rocket, and that rocket has to go with a very high speed, the so-called escape speed. That escape speed depends only on how massive the Earth is and how large the Earth is. And that leads to the following situation. You can take a look at this diagram that is more or less explaining the whole solar system and its layout. What we have here is how large the escape speed is at a certain temperature, and at that temperature also what the escape speed is for each type of gas. Or what speed the gas has. So as you can see here, Earth, Venus, Mars, and all these small objects, they have a low gravity, they're not very massive, and therefore their escape speeds are not that high. At that location, at that temperature, the escape speed is lower than the speed of hydrogen molecules or helium. Therefore, even if Earth wanted to keep them, Earth is not strong enough. It cannot keep the lightweight particles. They just simply escape into space at some point of time. They are like little rockets. They are able to escape into space. That's why all of that hydrogen and helium that was there at the beginning is not there anymore. Likewise, look at those beasts. These are the big gas and ice giants. They're really, really very massive, and they're mostly made out of hydrogen and helium because they can hold on to it. You see, they're so massive and so cold that their escape speeds are way higher than the average velocity of these gas molecules. That's why they've become so large, because they could hold on to all of that hydrogen and helium. Earth, Venus, and Mars couldn't do that at all. So therefore, it's not a surprise for us that there is no hydrogen and helium in the atmosphere. So wait. I showed you this picture of the Hadean Earth when we were bombarded by these asteroids over and over and over again. At that moment, there is no possibility for any kind of atmosphere. Everything is so hot that everything just literally either goes into space or is vaporized. You cannot have an atmosphere at that moment. So how did then the Earth get an atmosphere? Initially, there wasn't. It was without an atmosphere. And the idea is that, well, we get most of that stuff by volcanoes. What do volcanoes give us? Well, we can measure it these days. So if you check out what volcanoes usually do, they spew out a lot of material, as you can see here. Most of it is quite dangerous because there's no oxygen in it. And you can measure it. And on average, they give us a lot of water vapor, carbon dioxide, nitrogen, and sulfur, and a few other things that are not that great, but these are the main things that volcanoes give us. And that builds up over time the atmosphere, because remember, the Earth is able to keep water, carbon dioxide, and nitrogen because these are molecules that are massive and big enough that the Earth can actually keep them because they're slow-moving things. Hydrogen and helium would just go away. These, they stick around. So volcanoes slowly erupting, giving us a little bit of all of these ingredients, build up the atmosphere of our own planet. Really? I mean, dude, you're an astronomer, you can say that, but do you have any evidence for that? Because yeah, nowadays, this is what volcanoes do, but they must have been doing this over billions of years, so do we have any evidence that, I mean, who am I to tell you what happened 100,000 years, 1,000,000 years, or 1,000,000,000 years ago? There's actually one key proof, and that is really interesting. Remember when we went over the list of all of the things that are in the atmosphere, there's this noble gas, argon. Argon is really cool. There is one pathway to argon that we have discovered here on Earth. In fact, if you have potassium-40, this is an isotope of potassium, that is not stable. It can decay into argon. Now, there's a lot of potassium in all of the rocks of the Earth. Over long periods, that potassium is decaying into argon. Well, argon is a gas, a noble gas, but it's trapped because in the rock, because it's in the rock, right? It's not being released unless you have a volcanic eruption, and then it gets released, and once it's released, it's a noble gas, doesn't do anything anymore, and therefore it sticks around. And it turns out that when we measure what type of argon do we have in our atmosphere here in Earth, it's almost completely that argon-40. This is odd, because when we look at the sun and other objects in our solar system, and we analyze argon there, almost none of that argon is in the form of argon-40. So normally you would expect, if that came from somewhere else, you would anticipate that it should be like this, but it's completely like that. Almost all of it is argon-40, and that is being taken as evidence that most of our atmosphere must come from volcanoes. There's a little bit of discussion that, a lot of the water may have come from comets and especially asteroids. Okay, so, okay, let's take a deep breath. It's a lot of stuff that I'm throwing at you, so now let's relax a little bit. Take a deep breath. And you will realize that you have been putting a lot of oxygen into your system. Weird. Molecular oxygen that does not appear at all in that list of what the volcanoes give us. If volcanoes gave us oxygen, that would be great, right? You could go there and have a holiday and say, oh, yay, great oxygen is coming. No. These are deadly events because you're suffocating, because there's absolutely no oxygen that the volcanoes give us. In fact, it's very, very, very hard to naturally make molecular oxygen. Oxygen is extremely reactive. It does stuff, it corrodes things, and in nature to get free molecular oxygen is extremely rare unless it's being produced by life forms. And that is what happened. So initially there was absolutely no molecular oxygen in the atmosphere of our own Earth. And then it slowly rose because at some point of time, some algae, probably first bacteria, and then they were incorporated into algae, figured out that, there's a cool mechanism that we call photosynthesis, how we can generate things and generate a lot of energy. And the byproduct of that is molecular oxygen. They were basically producing this as a waste product of their own life cycle. And that's why we have that much oxygen in our atmosphere. It comes from life itself. And we utilize it quite well. So as you can see here, initially, almost no, so this is a logarithmic scale, over billions of years, there is almost no oxygen, molecular oxygen. And then once the cyanobacteria discovered this pathway, it rises very, very quickly, and nowadays we have about a stable, about 20%. It varies over time though. The great Carboniferous, when all those trees were on our planet, which we are now basically using as fossil fuels because at some point of time they got buried underground. So there was a lot more oxygen in the atmosphere. That's also the time when those giant insects were floating around because they are limited by their uptake of oxygen in the amount of oxygen that's in the air, and that enabled them to get much larger than they are nowadays. But by and large, it's about 20%, which is great for us because we need it in order to live. And the lesson there to learn is that, an atmosphere is not something that is static and kind of God-given. It evolves over long time scales, and changes can happen. Well, we are changing it at the moment. We can talk about this a little bit later on. But it's a dynamic system. And it's also a great system because it keeps our Earth much, much warmer than it normally would be. It's a super easy exercise in physics that I always tell my students, let's do this. You can calculate how warm should our planet be on the surface. It is being warmed by the sun. We know how much energy the sun gives us. And while we know how the Earth is losing energy by radiating infrared radiation, any object that is warm radiates energy, like a light bulb, like you. Everything that has a temperature is radiating energy away, and we can simply find the balance. The temperature is set by how much the Earth is getting from the sun and by how much it's losing. If you do this very simple calculation, you end up with a number that tells you that Earth should be completely frozen because it's too cold for liquid water to be there. So this is the so-called equilibrium temperature that you calculate. And therefore, you should think that Earth is actually like Hoth in Star Wars, completely frozen, an ice planet, because it's way too cold. Well, last time I looked at a picture of Earth, it doesn't look like this. We have liquid oceans, and it's much warmer than this. So why is that? And it turns out that is totally due to that atmosphere. And the way that this works is the well-known greenhouse effect. Everybody has probably nowadays heard about it. What happens here is that, the sunlight has an easy time to go through the atmosphere. It hits the ground, warms up the ground. That ground then gives you infrared radiation, and that infrared radiation should go back into space, but it has a much harder time doing that because it turns out that all these wonderful gases, carbon dioxide, methane, and also water vapor, they can absorb that infrared radiation. Meaning, what does it mean, absorb? Well, they take that energy and they keep it around a little bit longer, and therefore they're heating up our planet. And our planet is so great, it has liquid water and all of these nice amenities that are great for life because of that greenhouse effect. Without that greenhouse effect, things would be very, very bad. Most importantly in this game is, the most important role is being played by carbon dioxide. You've probably heard a lot about this. And remember, that is what the volcanoes give us. There's a lot of carbon dioxide that comes out. In fact, a big riddle is, where is all of that carbon dioxide? It turns out that most of the carbon dioxide is not in the atmosphere at all. It doesn't stick around there very long. It's actually in the form of rocks and sediments in the earth. So whenever you go to these great limestone formations, it's limestone. The carbon dioxide reacted with the water and turned into limestone. So everywhere in our planet, most of that carbon dioxide is actually stored in the rock. And therefore, we in fact have very, very, very little. Remember, 350 to 400 parts per million. It's very, 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 very little carbon dioxide, and yet it is super, super important for us. That carbon dioxide also has a big regulatory cycle. And that is a great thing about our planet Earth. It's a very active planet. The carbon dioxide that's in the atmosphere doesn't always stay there. It can be washed out because it turns out that liquid water and carbon dioxide are very, very reactive. You like Coke, right? Fizzy drinks, all of these things. You can put a lot of carbon dioxide into water. It really stores very, very well there. And when you do that, you form actually a mild acid, and that acid then erodes rock, and you have carbon dioxide-rich stuff that then gets transported to the sea. In the sea, it actually reacts with calcium to make those limestones. And that's awesome. That basically reduces the amount of carbon dioxide that's in the atmosphere and stores it somewhere here. And that would be the end of the story if Earth were not a super active planet. We have plate tectonics and volcanic eruptions, and that means that some of that stuff that gets stored doesn't just stay there forever, but it gets released again, and this is the great carbon cycle. This takes hundreds of thousands of years on average, but it's a very, very active cycle, and that active cycle requires a lot of things. It requires that there needs to be liquid water. Without liquid water, that doesn't work, because you have to dissolve the carbon dioxide. You have to put the carbon dioxide into something. It also requires that there need to be plate tectonics and volcanoes. Otherwise, all of that stuff gets stuck. I'm telling you this because we will see that some of that stuff doesn't happen on Mars. This is so great because it is actually our global thermostat. On summer days like this, I'm very grateful that we have AC. In the wintertime, I really like to heat my house. And all of this works in the same way with Earth. We have basically a thermostat that works with this carbon dioxide cycle. How does it work? If you haven't heard about this, it's a very quick explanation of the way that the temperature is normally regulated on our planet. Imagine for a few decades, it becomes cooler for some reason. We don't know why, but it becomes cooler on our planet. When it gets cooler, there is less rain. When there is less rain, less of the carbon dioxide gets washed out of the atmosphere, more of it stays there, And therefore, you have a stronger greenhouse effect, and therefore the temperature goes up. Oh, wait. That is counteracting the initial thing. This is called a negative feedback loop. Most people, when I tell them, oh, it's a negative feedback loop, they think, oh, it's a bad thing. No, a negative feedback loop is a great thing in this case. If it gets too cool, that mechanism leads not immediately, it takes about 100,000 years or so to regulate, but it regulates it in such a way that eventually it will heat up again. Likewise, if it gets too hot for a few decades, there will be more rainfall, more carbon dioxide can be washed out of the atmosphere, and therefore you have less left, and therefore the greenhouse effect is going to go down, and therefore it gets colder again. Again, negative feedback loop. It's just like a thermostat works in your house. You set it at a certain level, and if the temperature inside the house gets too high, your AC kicks in, and then it cools down, and at some point of time, your temperature sensors tell you that, oh man, it's freezing now, let's stop this. And then the outside heats the house up again until that cycle works again. So negative feedback loop works exactly the same way in the case of the Earth. Well, not always. Sometimes there are catastrophes. We know there are two episodes, one about 2.5 billion years ago, the other one just at the beginning or before the beginning of the great Cambrian explosion, where we have what is called snowball Earth. Catastrophically, things went wrong with this whole system. And for some reason, the temperature went way, 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 way down, and the whole planet was frozen. This is now Hoth. And the oceans were frozen to a depth of about half a mile. Surprisingly enough, life survived on our planet underneath in deep sea vents, hydro vents. Well, wait, how can that happen? What may have caused this? Well, sometimes there may be increased weathering because, remember, our planet is a very active planet. You've probably heard about this continental drift, and the way that our surface of the planet looks right now wasn't how it looked millions and billions of years ago. At some point of time, you have these supercontinents where all of these continental plates were basically shifted around like a big jigsaw puzzle in such a way that all of a sudden you form one gigantic, large continent. And the weathering patterns are now very, very different in those. In the central area, if you don't have rivers that are draining into the ocean, you will not get rid of that carbon dioxide there. And so the shape of all of those continents together, they can change things rather drastically, and that may have caused. So at least in the case of the one before the Cambrian explosion, we believe that was the case. So compare this to nowadays, right? Yeah, there's much more coastline altogether than here. Here you have one big coastline, but one big, really large landmass. Yeah, Asia is very large too, but it's broken up into much smaller pieces than here. So that can really contribute to that. How do you get out of that? It seems like a big catastrophe, and you're like, oh, whoa, now the carbon dioxide cycle has shut down. Now we are stuck. Gladly, we are not stuck, because the Earth remains active and volcanoes are still going to erupt. But now there is no precipitation anymore, and that carbon dioxide stays in the atmosphere. And what you get is you get more and more and more carbon dioxide. What happens with carbon dioxide is you're increasing the greenhouse effect, and you can get out of that snowball Earth. So maybe that is actually what cleared the way for this well-known Cambrian explosion, when lots and lots of animals started to basically happen at that point of time. So as you can see, even Earth is not such a great place sometimes for life. There are times in the history of our planet where things were really, really tough. I mean, to survive this snowball Earth, that's really difficult to do. And yet for most of the time of the lifetime of the Earth, conditions were really, really good. What's different with Mars? So when we look at Mars, we can also look at the same time, we can look at all of the terrestrial worlds. So we're going to include Mercury, Mars. We can even include our own moon. And we're going to take a look at our our nice twin, Venus. When we compare them, we can immediately see that Earth and Venus are rather large. Mercury and Mars are significantly smaller. And that has very, very big consequences. When we look at the surface of the planets, what shapes the surface of planets? Well, in our case, when you look at the Earth, that ancient surface that we used to have is not there anymore. We have erosion, and we have volcanism and tectonic plate movements. Our planet is an active planet. And it turns out that Mars, Mercury, and the Moon are not that active at all. When you look at their surfaces, especially the Moon, but also Mercury and Mars, these are old surfaces. Nothing much is happening there anymore because those objects have lost their internal heat. You can calculate how fast you're losing heat. So here's another quick equation. I'll just quickly go over the basics of it. How much energy you have depends on how much mass you have, how much volume you have. So this is something times the volume of the Earth. How much energy you lose depends only on how big your surface is, because you're basically sweating through your surface. It's the same with human beings, right? So you're losing energy through your skin, and that is the surface area. And if you take the ratio between those two, it turns out that, how long does it take to completely cool down? That depends on how massive and how large you are. Large objects are cooling down more slowly. Well, makes sense, right? If you have a huge cake in the oven and you take it out, or turkey, right? Thanksgiving, you have a huge turkey, it takes quite a while to A, heat it up, and then to B, cool it down. If you have a tiny little thing, you heat it up, and that cools down very quickly. Also, things that are hot are cooling down faster than things that are cool. It's also an interesting thing. And that means that, all three of the small objects, the Moon, Mars, and Mercury, they have cooled down way more than the Earth has. And that means that their crust is rather large and rigid, and there is no such thing as plate tectonics. So Mars cannot have the same thing that Earth does, because it's too small and it has cooled down already in the interior too much. In contrast to that, Earth, as well as Venus, being almost the same size as Earth, they have enough material that they haven't cooled down very much. And that drives all of this wonderful plate tectonics and volcanism and all the activity on our own planet comes from the fact that it is large. The atmospheres of all of those objects, they probably started out the same because they had volcanoes. So Mercury, Venus, and the Moon, they had volcanoes. And that means that they all started out basically almost exactly the same. But then their history, their evolution of the atmosphere turned out to be very, very different. What happened on Mercury? Mercury is very close to the sun and is very small. It can immediately not hold on to any of the hydrogen and helium, but also all of the other elements, it cannot hold on to these, and therefore it loses them. And it turns out that, well, obviously, when you nowadays look at Mercury, it's like our own moon. It has no atmosphere whatsoever, has lost all of it very quickly because it's too small and too close to the sun. Venus is still closer to the sun than the Earth, and that has a dramatic consequence. It turns out that on Venus, it's hot enough that you cannot have liquid water. At no point of time early on were there oceans. And that means that carbon dioxide thingy that happened on Earth, where everything turned into limestone, did not happen on Venus at all. All of that carbon dioxide stayed in the atmosphere, and the volcanoes gave it more and more and more and more, and you're ending up with a runaway greenhouse effect. You end up with an extremely dense carbon dioxide and nitrogen atmosphere. All that water is lost through chemical reactions and photolysis of the sun's rays, and you end up with a hell of a planet, basically. Despite the fact that it's called Venus, the goddess of beauty, it is tough to be there because it is extremely hot, bone dry, there's not a single drop of water, you have sulfur clouds, it's hell, basically. Earth, awesome. Earth is this Goldilocks type of planet. Everything ended up being in the right place. At the time of formation, we are able to hold on to water, and the temperature is just nice enough that it can rain and water can condense and very quickly form standing pools of water. We end up with oceans, and into those oceans you get all that carbon dioxide. So you end up with very, very little carbon dioxide. You end up with a very mild greenhouse effect that just keeps it warm enough so that there will be liquid water, and so we end up with this wonderful planet for life. Well, now you go out to Mars. Mars is a little bit farther out, and it's much smaller than the Earth, and you end up with a catastrophe. Starts out the same way, but then Mars is cooling down because it's farther away from the sun. Most of that carbon dioxide then also goes into rocks. But then, unfortunately, it gets cold enough that water is not in the form of oceans anymore, but it's ice. And at that moment, you shut down everything, basically. And unfortunately for Mars, you also shut down the internal mechanism because there's not enough heat anymore. It cools down, and you lose most of that atmosphere because Mars cannot hold on to it. It's too weak. It's not massive enough. And furthermore, at some point of time, Mars loses its magnetic field. That's a big blow because now the solar wind and the cosmic rays can impinge even more on the atmosphere and strip away all of that carbon dioxide and nitrogen. And you end up with a very, 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 very tiny little thin atmosphere. And that obviously is a really big problem. So you see, you start out exactly the same. All those planets started out, volcanoes give you carbon dioxide, nitrogen, water, argon, oxygen. No, oxygen you don't get. You don't get that other than life. And yet, depending on where you are in the solar system, closer to the sun or farther away, and how big you are, like the Earth and Venus, or small like Mars, you end up with completely different scenarios. Only Earth is the Goldilocks planet. Mars and Venus suffer from these big problems of either a runaway greenhouse effect that makes it a hell or a cold, dry desert. And that literally means that Mars has a massive problem. It is not massive enough currently to do all these great things that provide the stability of us living forms here on Earth. Yes, it has an atmosphere. It's mostly made out of carbon dioxide, but it's only 0.6% of the Earth's pressure. Tiny little thing. It's like you're living twice the height of Mount Everest. So, not good. That immediately renders the surface conditions with the temperature and pressure such that there is no liquid water possible. It's either ice or in the form of vapor. The core has cooled down because Mars, as you can see, you would think that, oh yeah, well, it looks actually big, right? It looks almost as big. Well, I mean, it's not that small. But remember, what matters here are 3 dimensions. So it has, well, as you can see here, well, more than half of the radius. Well, but 1/2 times 1/2 times 1/2 in 3 dimensions is about 1/8. And that means that, oh, look at this. It only has about 10% of the mass of the Earth. It's a tiny little thing compared to the Earth. It's a small planet. And Furthermore, that leads to the fact that it loses its magnetic field. That's a big problem. The soil there mostly consists of perchlorides. Also, there are very fine dust particles that get kicked up all the time. If you've ever been out in a dust storm, that's really bad. Mars also doesn't have a moon. That will come in very interestingly as well. So it has two tiny little moons, but not a large moon like our own Earth. So that means there are a lot of problems. If you want to grow plants or anything, you need light. Right from the bat out, you get only about 60% of the light that you get here on Earth, simply because Mars is farther away from the sun. Building structures, probably not that easy because it has a very low surface gravity, only 40%. The atmosphere, as little as there is completely unbreathable for human beings. So you need to bring your own oxygen unless you make it over there, the oxygen. And because the atmosphere is so thin, you're bombarded by cosmic radiation and the ionizing solar radiation. It's very, very cold compared here to Earth. Furthermore, the chemical conditions, both in the soil as well as in the air or the atmosphere, are such that organic molecules are broken down. Not a good idea if you want to live there either. And there's no magnetic field that protects you from the solar wind and the cosmic rays, simply because it's too small. So, well, if you want to live there, you have to solve all of these problems. And these are massive problems. It's not like, oh, well, we need to build a little greenhouse and that's it. No, you have to do this on the whole global scale. The first thing that you need to do is you need to increase the size of the atmosphere and the density of the atmosphere. You need to bring in a lot more atmosphere. Because the big problem that is there on Mars right now that would require total life support systems is that at the current situation, the pressure at the ground level is only a tenth of the so-called Armstrong limit. What is the Armstrong limit? The Armstrong limit is that water starts boiling at your body temperature. And if you make the pressure less and less and less, water starts boiling at a lower and lower and lower temperature. At some point of time, if the pressure is too low, it will boil at body temperature. Exceedingly bad when you are surrounded by air that has only that pressure. Because it turns out that everything that is liquid on your body that has contact to the air will boil. Meaning your tear ducts and your tears start boiling. The water on your tongue starts boiling, and you can't do anything about it. They actually did tests in the 50s with subjects that got paid money, where they subjected them to low density, and they were supposed to describe, what do you feel? And most people said that, well, before I passed out, I felt this weird burning on my tongue and my eyebrows. I mean, yeah, that was the water that is burning. So if you have an air pressure that's even less than that, you need to be in a pressurized suit. Otherwise, you die immediately. That is why fighter plane pilots have to have these pressure suits. It's not for oxygen or so. No, it's to prevent that effect. They're flying high enough that at that height, they reach the Armstrong limit, and they would literally burn. So that's why you need these pressure suits there. So we need to increase the pressure of the atmosphere on Mars, globally on Mars, by quite a lot. So, well, there is carbon dioxide, right? I mean, we've seen that there's frozen carbon dioxide. The polar caps are mostly made of frozen carbon dioxide. So why not release that? Why not put it in the air? That is really the idea that Musk has, Elon Musk. He says, oh yeah, let's just kick up all of that stuff that's in the ground with giant nukes. So we're nuking Mars, and therefore we will increase the atmospheric pressure because we are releasing all of that carbon dioxide. Well, there are many drawbacks to that. You can't even list all of them. Much of them actually have to do with the fact that it doesn't do the trick at all, because that settles after a while again, and it will be frozen again because you're not raising the temperature quickly enough. Also, the dust that covers the planet for probably a couple of 100,000 years will lower the temperature even more. Another idea is to do it more gently. So people have proposed that you could float giant mirrors around Mars. They need to be about the size of 125 kilometers in diameter, so about 80 miles. Yeah, let's build a giant mirror and transport it. It seems a little outlandish for me at this moment. Also, kicking up all of that carbon dioxide doesn't really solve the problem that in order to live there, you need to breathe oxygen. Well, there's still no oxygen at that moment. So there are other ideas that have been proposed. We could actually capture stuff from the frozen outer parts of the solar system. So let's say on Titan, there are a lot of hydrocarbons, and we can how do you transport all of that stuff? And this is not a little bit. It's not like, oh, you're taking a container of that gas and you're dumping it on Mars. No, this is massive amounts of it. So at the current situation, I don't see any kind of mechanism there. We could export CFCs. We were very good in the 70s to the about 90s in producing these. Remember, we had them in the fridges and all of that. This caused actually a huge problem here on Earth. We've solved that problem, luckily enough. We could do the same on Mars. We could transport all of the CFCs, and that would increase the greenhouse effect. It doesn't solve the oxygen problem, but the problem is that, well, between 72 and 96, we produced about a third that would be needed to raise the temperature on Mars by just a few degrees. It's completely bogus. And these things are toxic. So you don't want to have them hanging around in the atmosphere of Mars. Once we have achieved that goal, as I told you, we still don't have any oxygen. We need somehow more oxygen there. So not only do we need that, but any kind of livestock and or plants will require oxygen. The problem there is that, well, how do you raise anything when the toxic soil is a big problem? Probably not even cyanobacteria could survive there. And all of the life forms that we know here on Earth require water, liquid water. Where is that water? Well, at the moment, it's not there. It's frozen, it's in the form of ice, but the temperatures are such that it will never be unfrozen. If it does unfreeze, it goes into a gas form, not in a liquid form. And that also takes probably a long time. If we looked at the evolution of oxygen in our atmosphere, that took billions of years. If you really want to colonize Mars in the next 50 years, you don't have billions of years to do all of that. Also, since there is no magnetic field, you're bombarded with all these cosmic rays and UV radiation that will lead to high cancer rates and or mutation rates. And we could breed some kind of bacteria that are radio-resistant, so-called radio-resistant extremophiles, but they're certainly not livestock that we can eat. So these are all very, very big problems already. Additionally, there are problems, as I said, of the harmful radiation. There are solutions for that, interestingly enough. So it's kind of cool that people are thinking about, how could we give Mars actually a magnetic field? And when I first heard about it, it's like, wow. If you place a 1 to 2 Tesla magnet at the so-called L1, Lagrange point 1, it would induce a magnetic field that is strong enough, comparable to the size of the Earth's magnetic field. 1 to 2 Tesla is not too bad. We can generate this here in our MRI machines, but it's kind of difficult to understand how we could get an MRI machine at the Lagrange point here at that moment. All those problems do not solve the general problem that Mars is simply too small. It has cooled down so much. It has no plate tectonics. Therefore, whatever you do, that wonderful negative feedback loop for carbon dioxide does not work on Mars. And so whatever you do, you have to keep doing over and over and over again. We have to be the driver of all of this. We cannot rely on the planet to do it itself. I mentioned there is no moon, no large moon. Well, it turns out that the moon actually stabilizes the Earth's rotation in such a way that we have stable seasons. Mars also is tilted, so Mars has seasons, but there are large variations. Those variations in the case of the Earth are damped because of the existence of a very large moon next to us, and therefore it has been stable for very, very long times. It turns out that over long periods of time, the variation in Mars tilt is much, much, much larger because it lacks this large moon. The soil is toxic. If you've ever tried to detox anything in your backyard or so, it takes ages, right? Now you want to detox a whole planet. Sounds actually like Dune to me somehow, to be honest. And here's a warning example. Has anybody ever been to Arizona and the Biosphere 2? Do you remember that experiment? Yay! So this was a crazy experiment, I think, mostly in human psychology. I mean, the fact that those guys didn't kill each other is pretty crazy. But we weren't able to actually, when we have full control over everything. So if you don't know what this is, they tried to have a closed ecosystem where everything was being generated basically within this large area. So they had a jungle area and plants and this and that. So they were trying to see whether they could basically live in autarky without any contact to the outside world, and that completely failed. I mean, the levels of carbon dioxide went up way too high, and it was a giant disaster basically. And we realized that even though we have full control here, we have all the resources available to us, and if we enclose it in an area, we can't even run anything like that on a small scale here on planet Earth. And now you're telling me you want to make a whole hostile planet that has a host of way, way, way more problems than whatever is inside of Biosphere 2 and turn it into Earth. So you want to make Mars like Earth? Already the acronym doesn't work, right? This nonsense. Therefore, I mean, and I'm not, I mean, so you could think, oh yeah, you're biased. Yeah. This is the consensus among basically all astronomers. And already in 2018, Sir Martin Rees, the royal astronomer from England, he is quoted here with, the only reasons for humans to go to space would be for adventure. You're not going to settle anybody there. The idea to have 1 million people settle on Mars is a dangerous delusion. This way surpasses all of the resources that we have, and for most of the problems, we don't even have a solution yet. It's utter nonsense. Therefore, I have a much, much, much better proposal, and I would say that we make Earth great again. And I already have the right cap for that. People told me I should do merchandise with it, and I could probably become rich, but I have not started the production of this. My wife actually tells me that you're falling short here of one letter. Make Earth great again now, which spells Megan, and that's her name. So that's what I should do, actually. Okay, if you have any questions, please. You've been sitting very patiently now, and I've thrown so much stuff at you. Now it's your time to ask me. We want so that the people can hear.
Looking back at the asteroid that came from Mars, not the asteroid, the meteorite, how do you know, since it's so old, that the evidence of the bacteria was from Mars or after it got here on Earth?
Yeah, you've put the finger in the wound. This is one of the debates that everybody has, is they're like, well, this thing landed in Antarctica, we found it in Antarctica, and we know that there are cyanobacteria and other bacteria in Antarctica, and how do we know how long it's been sitting around there, and are these possibly contaminations from Earth itself? So that's one of the big problems there, yes, and there are many, many other ones. So again, this is point in case for, this is not conclusive evidence, neither for nor against it. It's just one basically piece of the puzzle at the moment, but that's a very good one, yeah, definitely. And that's always the problem with these types of things, when you're like, okay, well, contaminations with Earth immediately when you're in contact with a planet that is extremely rich in life, you will always contaminate it to a certain degree.
Is this all mine? Can you hear me okay?
Yes.
I enjoyed this talk very much. Thank you. There's a tremendous amount of information packed in here.
Oh, and by the way, I will make it available for Zach, and you can actually take this. So it's probably on the website of the library, and you can take all these slides if you want to, and if you can look at them again. So yeah, thanks for reminding me of that.
Are we?
Yeah.
I'm not sure how the main portion of your talk ties up with some of the themes that you raised at the beginning. Here's why. We consider Earth as a physical system. We talk about the physics, the chemistry, we talk about the thermodynamics, we talk about the mass energy density of the atmosphere, we talk about it as a physical chemical system. And then we compare and contrast that with the physics of Venus. And we learn that they're very, very different. And so one conclusion might be that Venus is not, or Mars is not hospitable to our form of life. That's fine. That's about us. We're a carbon cycle. Out in Andromeda, life might be instantiated in a nitrogen cycle. We who worry about this stuff really are puzzled about the relationship between the physics of a system, on the one hand, and whether or not it's alive, on the other. Think of HAL in 2001. It's semiconductors and copper. HAL is conscious. It's controversial, but a lot of people believe it. So my question to you is, what inferences would you want to draw as a working physicist? What inferences would you want to draw about the relationship between the physics of an environment, on the one hand, and its hospitability to life, on the other?
Oh yeah, that is actually a very deep and good question, and I'm glad that you're bringing this in with HAL, for example, because one thing that I didn't mention at all, of course, is, or I did mention a little bit, is we have robotic missions to Mars, and we've landed there already. And well, fast forward maybe 50, 60 years, if we develop something that's in AI that basically could also be called, to a certain degree, intelligently alive, we could plant it there, and then yes, that definitely then opens up a completely different parameter space. And yes, I mean, I totally agree that we are narrowly focusing basically on, what have we learned about life here on Earth, and then we basically extrapolate this to other places. And one of the key things always is that, well, there's no liquid water, therefore it doesn't work. There are ways potentially around it. Part of the way that I was trying to, when I was thinking about basically the punchlines of my talk, is that, of course, the idea was, well, terraforming Mars. If we want to live there, we need to make it a little more like our planet, and that was the basic punchline there, basically. So, but I agree that once you, and I'm not a specialist in this at all, but once you look at biological processes, what you can even call a biological process, it becomes very difficult very quickly. And
think of microscopic as Andromeda strain. There's a point at which, when you're tracking the complexities of this bacteria or virus or whatever it is, one of the researchers said, "My God, it's alive." Well, you know, it's not sustained by the sorts of things that sustain you and me. But it would be bigoted and prejudiced to require our biochemistry for life.
Right. Yeah. And that's why I said that's why I called it terraforming Mars, with the explicit goal of, we want to go there and live there, which, as I said, I think at this moment is a folly rather than feasible. But I agree with you that once we search for life somewhere else, we need to be very open to very different possibilities, and that's part of the big trick of well, how can you imagine something that is almost unimaginable from our perspective? It's a difficult task to do.
We have time for a couple more, so I'll go over here.
Hi again. Thank you for the talk. One quick question: why did the heavy bombardment end many years ago? We don't have it anymore.
Well, part of the big reason, of course, is that you have a limited number of these objects floating around, and once they collide with each other, well, they're gone. And so after a while, you clear up all of that debris, basically. So during the formation of the solar system, there's a leftover of lots and lots and lots of these objects. But yeah, if one collides with the Earth or with Jupiter is much better in capturing all of these things, it's gone. And so after a while, you simply clear up most of these. Another one is that many of them are then kept in orbits that basically prevent them from, so Jupiter very often prevents them from getting into orbits that would be Earth crossing or so, and that contributes to it as well. But it's mostly about the fact that, well, there are fewer and fewer objects that can have such large impacts. We do know that so this catastrophic event that wiped out the dinosaurs, that should happen about every 100 million years here on Earth. And these are very large asteroids or meteorites. But the really, really, really big ones, after a while, they're simply gone. And that's what ends it, basically.
Yes, I thought you did an excellent job proving that.
Oh, no, I didn't prove anything. I just presented.
Your evidence was very strong. I know can't be 100% on things, but your evidence was very strong. I agree with you about the whole delusional thing and to make Earth great again. I guess my question would be, even if there was a different sort of artificial intelligence or consciousness that could live on Mars, other than to entertain us or study it or whatever, or observe it, I mean, what would be the point? I mean, if we could bring back some kind of minerals or something from Mars that would benefit us on Earth, I don't know what the point of that would be, other than knowledge for knowledge's sake or whatever. But yeah, I think things have been fast forwarded so much we can't reverse, like your presentation said. At one point, maybe there could have been life on Mars, but it's too late now. And the point is, we need to save Earth before we boil or freeze.
Yes. Yeah. No, I totally agree with that as well. Yeah, indeed, although, as I said, I mean, there was this one point at the very beginning. So I've always been also interested in, and it brings back your point of contamination as well. So there's another place in the solar system where astronomers are really interested in this, and this is Europa, one of the moons of the outer solar system, the moons of Saturn, and we believe that underneath of Jupiter, we believe that underneath the icy surface there could be a very large ocean that could harbor life, because the conditions could be like the early Earth with these deep sea vents. And one of the ethical questions there would be, well, if we start exploring this, the consequences could be that we destroy this type of life, because most contacts between life forms end tragically, and there's a whole ethical question related to that. I mean, if it were that there were intelligent creatures on Mars, what would we do, right? I mean, it's a very deep, I think, ethical and philosophical question. Luckily enough, we don't really have to think that much about it, because we haven't found anything that's more than potentially microbial life, but if it were, that would raise another whole point that I haven't mentioned here at all. So yeah, there are many more aspects to all of this. I could fill, I mean, probably a whole semester or so with some of that stuff. So.
I've got a quick question. So you went over, some of the fantasies that people are interested in, such as nuking Mars and introducing carbon. On your last slide, make Earth great again. Do you know of? I know there's like carbon capture and all that. Like, what are people focusing on making Earth great again? Like, how can we fix what we're doing to our current atmosphere? Are you aware of any large,
there are many
big idea program?
Yeah, there are many big programs and ideas about carbon capture. Yeah, that's probably one of the big fields. But also, it does turn out that when it comes at least to the energy production, we do already have the technology, right? We just need to implement it. We know how to make clean energy, and it's just a question of, do we want to, and are we willing to invest these large amounts of money into it? And that's I think where the whole politics then comes in, and economics comes in, and it's a large problem. I mean, it's as you can see, it's already large enough here on Earth where we can control it because it's right in front of our door, and we are the ones responsible for it. So trying to do this on Mars is stuff for the future. We should first do it here. I totally agree.
Well, Dr. Stephan Frank, thank you so much for this presentation. If anyone wants to stay and ask questions, you're more than welcome to. Just a quick reminder, we will be back next Thursday, July 17th, for a second astronomy program, and then the following Thursday, the 24th. So whole new talk. We hope to see you back again. Thank you again, Dr. Frank.